This new series of videos is going to be on the mechanical system. We're going to talk about liquid refrigerant, vapor refrigerant, what the pressures and temperatures have in relation to each other, how we diagnose equipment utilizing, superheat and subcool. The entire series of videos that we're going to be releasing are going to get you to level up one video at a time so you can better understand superheat and subcool, better understand evaporator coils and that coil technology, and condenser coils and that condenser coil technology, pressurized with compressors, how important they are, and the metering devices that bring those pressures back down. So stay tuned. Okay, welcome back everybody. We're going to talk today about refrigerant cycle. We're going to be releasing a series of videos on compressors, metering devices, evaporator coils, condenser coils, just the mechanical system itself, how it operates, some of the confusions that are in the trade, and the improper diagnostics, and how we quickly kill compressors because things aren't charged properly. We're not boiling that vapor or that refrigerant off to a vapor when that refrigerant comes back to the compressor. So I don't want to start off on a heat pump or start off on any one specific type of unit. When you look behind me, this kind of looks like it's not complete. There's no metering device here. Looks very, very basic, and looks like this may not be anything that you can really benefit from, but I'm here to tell you to stay tuned on this, because you will. When we look at evaporator coils and condenser coils, the things that we look at are what the line going in and the line leaving, and everything else that's part of that coil we just simply forget. We don't think it's important, and we easily misdiagnose. So I want to start off with a small section of these coils and then just grow your understanding on what's really going on here. So if we just looked at a very basic, we got compressor. I've got blue on one side, red on the other side. That represents low pressure, high pressure. The condenser coil, I have a dryer. This is just a one-directional dryer, and I have an evaporator coil. A couple fan motors just to represent that, there are motors here that are going to be moving air over these coils. I'm going to go ahead and just draw out the refrigerant circuit, that you may already know. Let me go ahead and just get right on into it. If we took our discharge out of our compressor, we're basically going to go right into the condenser coil. As that refrigerant flows through that condenser coil and there's air moving over it, we are condensing that refrigerant to a liquid state. And so when we come out of there, I'm just going to move my mark down a little bit smaller. It's going to come out of here and go right into the dryer. Now we have liquid refrigerant going into a dryer. This dryer has the ability to create a pressure drop because it's restricting at this point. There's no metering device here, so I'm just going to say this is just a capillary tube dryer. I'm going to go ahead and move my mark down a little bit more, and we'll come out of that dryer and we'll feed the coil. Okay. As a matter of fact, I'm going to go ahead and do that in a different color. I'm going to say that that's going to be a low pressure. And so we're going to feed our coil now a low pressure liquid. Coming out of that coil, I already have my next mark set up for me. We're going to come out of this coil and we're going to leave and come right back to the compressor. And so now I'm not talking about any types of pressures, governing what type of refrigerant we're using. Let's just go off of what state we should be in. All right, so up here I'm going to say that this is a vapor, and down here this is a liquid. Going across the dryer, we are still a liquid. Okay. Smaller line, it's being metered here. And as that refrigerant enters that coil, that air moving across is going to boil it off. And so when we come back, we are going to be back in a vapor state. And that's basically the bare bones of it. It doesn't matter what type of refrigerant, if it's for a cooler, a freezer, for an air conditioner, doesn't matter if I have an expansion valve, if I have a capillary tube system, a piston, EEV, electronic expansion valve, anything like that, just a cap tube dryer, it doesn't matter. The whole point of this isn't what the pressure should be. The whole point of this isn't what refrigerant we're using. It's supposed to be, we understand that it enters the compressor in a vapor state, it leaves the compressor in a vapor state. It leaves the condenser coil. I'll go ahead and label these parts here. It leaves the condenser coil in a liquid state. Okay, goes across our dryer, and it is now, it's being metered here. We'll just call this a cap tube. And then as we enter the evaporator coil, we boil off that liquid back to a vapor, and then we leave the evaporator coil a vapor. That's basically it. And so we can look in the book, we can understand this. It's a very simple drawing, and you might be asking yourself, what am I going to learn out of this? Exactly. So let's go ahead and look at a couple of things. I'm going to erase this, and we're going to draw this one more time. Okay, we know our components now. We don't have to write that back up there. Compressor, motor, condenser coil, dryer, evaporator coil, blower motor again. And so if we were to insert a metering device, let's say it's just a piston, right? Say there's a piston inside of there. And we'll draw a little piston in there so everybody's comfortable. We'll just say there's a little piston in there, right? And we said that we're going to come out of here. We're going to enter our condenser coil in a vapor state. We're going to leave our condenser coil in a liquid state. We're going to move through the dryer, and then we're going to come out of the dryer. Now notice I'm red because we haven't metered until we go to our metering device. Okay. We are still in a liquid state. This whole process, that's why it's called a liquid line dryer. Now, there is a pressure drop at this point. So we go from high PSI to low PSI. And now we enter the evaporator coil. And at this point, we boil off back to a vapor and then back to the compressor. And what happens here, if we are a vapor state here, we are a liquid state. All right, and so the compressor's designed to pump refrigerant in a vapor state. All right, we have to leave the condenser coil in a liquid state. We have to enter the evaporator coil in a liquid state because we can't get vapor from vapor, right? We can move vapor, but we're not going to remove any heat unless we're actually boiling off. We have to flash off. There has to be a state of change. So this liquid has to enter this evaporator coil for it to boil off and that vapor return back to the compressor. And so if we look at that, basically, the simplest way to look at this is one critical point. This is the second critical point. And so I'm going to now put some pressures on this board. Let's just say blue, red. All right. So say if we just said we're dealing with R410A, we'll just write R410A here. And we'll say our high side, for example, was 325 psi. Okay, we know it's 325 psi. It's in a vapor state. Well, we're condensing that vapor down to a liquid, but we have not changed the pressure. So we're still at 325 psi. We're just now in a liquid state. Now that liquid moving across that dryer, there's no pressure change at all. There's no state change. We're still in a liquid. By the time we get to that metering device here, there is now a pressure drop. So on one side of the metering device, we're going to be 325. And we'll just say on the other side, we're going to be, let's just say we're going to be 145. We can do that. So we have 325 on one side. We have 145 on the other. That metering device is what created this pressure drop. It didn't change the state. We were liquid going into the metering device. We're liquid leaving the metering device. We have to be liquid to go into the evaporator coil so we can boil off back to a vapor. However, there's no change in pressure. It's just 145, right? And so we don't change pressure until we get compressed in that heat of compression. You know, that brings that temperature up, and then now we're going to start leveling up. We're going to start getting to the temperature. What is the temperature related to 325? Well, 325 is going to represent 102 degrees on a pressure temperature chart. Excuse me. I'm going to use a different color here. So this is going to be 102 degrees. So we know three values here. We know 325 psi. We know 102 degrees. And we know that we're in a vapor state. All right, so when we come down here, we're at 325. So the theory that we are in a liquid state is still a theory because our saturation point is still 102 degrees. We have no proof that we're a liquid because we are 102 degrees here and we know we're vapor. We also have no proof that we're vapor. All right, so we have no proof that we're liquid. We have no proof that we're vapor, just off the pressure and the temperature that's related to that pressure. That's where I want to really bring to your attention where you think you know what you're talking about, but you're misunderstanding a simple step. Here we're 325. That 325, it represents 102 degrees. We come out of here at 145 and the temperature at 145 degrees or 145 psi is 52 degrees. I'm going to write 52 degrees here. All right, so the temperature related to this pressure is 52. All right, so now we have basically a 52 degree coil. We can definitely say that because the coil is 145 degrees. So if the coil is 145 degrees, we know it's definitely 52 degrees. And if it's 52 degrees, then any air that's warmer than that going across that, obviously we're going to exchange heat. We're going to have colder air. We know that. But there is no proof that we're in a vapor state just because we said we're at 145 degrees. Because how do you know that that 145 still isn't 52? And so here's where we need that extra value. We need to know what that superheat is. We need to know what that subcool value is. And once we can achieve those values, then we know without a shadow of a doubt that there's no more theory. There's proof that we actually produced liquid, and there's proof that we actually produced a state of vapor. And so going off of pressures alone and saying, yeah, we know how this works is not enough. It's just a theory. Okay, we know our compressor is working because we have good compression ratio. You know, we obviously picked up heat of compression here. You know, that's great. We know we're getting cold air, right? Or we have cold air coming off the coil because we're exchanging heat. But how do you know your compressor is not having liquid come back to it? How can you guarantee that your condenser is condensing the vapor, okay, and is actually cooling that down enough to where there's liquid? Because the pressure does not change. Nowhere does the pressure change until you go across the metering device and you come back across the compressor. So we have a pressure rise, we have a pressure fall. So here we'll say pressure fall. Up here we're going to say pressure rise. And if pressure rises, temperature rises. If pressure falls, temperature falls. So we can also say temperature fall, because those two are related. Up here we can say temperature fall, or temperature rise, excuse me, because those two are related. 102 is the value of 325 psi when we're moving 410A refrigerant. Okay, 145 is the value of 52 degrees when we're moving 410A refrigerant. So how do we know without a shadow of a doubt that we actually have vapor leaving the evaporator coil and liquid leaving our condenser coil? Well, that's where we get into subcool. And that's where we get into superheat. And so just very simply, we have to make sure that we are cooler, even though there's not a pressure change, we are cooler by temperature more than the 102 saturation point of the 325. So if we were to just kind of clamp right here and say we were reading 96 degrees. Well, 96 degrees, well, simple. You have 102. This is your LSAT. And then you have the line temp at 96. I want to subtract those two, and we gain 6 degrees, and this would be our subcool value. And so now if we can read a difference in temperature, even though the pressure did not change, then we now have proof that we have cooled down the refrigerant beyond what the pressure or the saturation point suggests. Now we know we have liquid leaving. This is the only way to guarantee that there is liquid, is by reading a subcool. That's why you cannot go off of pressures. It is not enough information. You cannot go off the saturation temperature. It is not enough information. You can't go off the theory that, yeah, we condensed vapor to liquid, because off of that, you don't have proof that you did that unless you can read a subcool. Now, coming back over here to the superheat, all right, if we're entering our coil at 145 psi liquid, now that we can guarantee that it's liquid, okay, and we have 52 degrees related to that, how do we know we boiled off? How do we know that we don't have a liquid coming back? Okay, because we have 145 down here at 52 degrees, and guess what? It's in a liquid state. So how do I know that this 145, 52 degrees, is not a liquid state? I have to see if there's a temperature difference. So if I were to clamp this and read that, then I would say, okay, well, my vapor saturation is 52 degrees, and my vapor line temp, okay, let's just say it read, I'm just going to say it read, say, 65 degrees. Okay. All right. So same thing. I want to see what is the difference on that. Well, the difference on that would be, let's see, 65 minus 52. That would be 13. And I would say that would be my superheat. 13 degree superheat. All right. So I'm reading 13 right here. Okay. And so now I've said that I'm reading 65 degrees coming out of here, I have picked up 13 degrees of heat beyond the 52 degrees. That is proof that I am in a vapor state. That is proof that I have boiled off and I am in a vapor state. And so just looking at that superheat, the vapor line temperature, the VSAT, taking the differential, giving me a number. Now let's just say that number was still 52. Temperature here is still 52. Okay, well if that's 52, or it's less than 52 and I'm in a negative superheat, if I'm 52 here, then that means I'm zero superheat, which means there is no proof that I am not returning liquid, and I have to return vapor. So it's vapor in, vapor out, liquid out, liquid back in. Now this gets a little bit more complicated when we start getting into other sections of coil. So I'm going to go ahead and erase this, and we're going to write it again. And there's a lot of confusion on what pressure should I be at? What should be my pressures? Well, I'm going to tell you right now that if you're asking the question of what my pressure should be, then you need to go back to the drawing board, because that's the wrong question to ask. You should be asking, what should my superheat be, and what should my subcool be? Okay, so now we're back to bare bones here, and what I'm going to do is I'm going to go ahead and just move another section of coil down here, and give us 2 sections of evaporator coil and 2 sections of condenser coil. Now we're going to draw this one more time, and we're going to say our discharge and our, oops, yep. I'll go back here. All right, so we're going to say we're going to come out of our compressor, and we're going to come down, and we're going to tie in to our condenser coil in 2 different sections. All right, let's see how we did that. So now I have, and I'll go back and put some pressures back up there. We'll say we're a state of vapor. We'll just go ahead and do another example. We'll say we're 305 psi, a vapor state. The temperature related to that is 98 degrees. So those are our 3 values. We have 305 psi. We're dealing with 410A. So we're just going to write R410A. Doesn't matter the refrigerant. All right, so we have 305 psi, vapor state, 98 degrees. That's what's coming into the coil. So let's go ahead and draw some arrows here. Okay. Now we're going to have to leave the coil. Okay. So I'm going to just leave the coil on this side. Okay. So we're going to leave the coil here, and we're going to leave the coil here, and I'm going to tee in to my liquid line, and that's going to come over and go into my dryer. Okay, so over here I'm liquid, still the same pressure, and still the same saturation point of 98 degrees. Okay, we have no proof that we're liquid. We just know that the pressure is the same, because nothing here is going to change the pressure. As long as you don't have a restriction, nothing is going to change the pressure. Absolutely nothing. Absolutely nothing. Okay? You're not going to have one pressure here and a different pressure here. I don't care if this coil was bad. If that motor shut off, your pressure is going to rise here, correct? Right? You'll read it leaving the unit, but that pressure is the same all the way back to that compressor. So if the pressure rises here, it's the same over here. Everything here is going to be the same PSI. Everything. That pressure will not change until you get across that metering device. So we're going to go ahead and come out of our dryer. We're going to hit that metering device. Okay, we're now going to have a pressure drop. Call it pressure fall, pressure drop. And now coming out of this, we automatically know that we're going to enter into the coil. See, now it starts to look like we have some capillary tubes here. We're going to enter in the top section of the evaporator coil and the bottom section of the evaporator coil. Two different coils, two different coils. All right? We just added more capacity is all we've done. Okay? The ability to transfer more heat in a given amount of time. And so leaving these evaporator coils, right? I'm going to just kind of leave on this back end over here. I'm not going to do the whole, back and forth, back and forth. It's just, this is more stuff on the board. Let's just deal with boxes for right now. When we get into coil technology, then we'll start getting into that. And so we're just going to tee into a process tube, right? And that's going to come over and go right back to our compressor. Just as simple as that. And now we'll start looking at some of these values here that we talked about. We know that we're going to be vapor here. All right. If we had to pick a pressure, we can say that we're 135 psi. If we wanted the temperature at that, we'll say that that is 47 degrees. And so we know that we're 135 psi in a vapor state. We're 47 degrees. We don't know 100% yet. Let's just continue to write these down. Over here, we're at 305 psi. The saturation temperature at that is 98 degrees. Okay. Obviously, we know that the state that we're in is a liquid state. We're leaving that dryer in a liquid state, same pressure. We're hitting that metering device. And the moment we get on the other side of this metering device here, we're liquid still. Still liquid here. However, we had a pressure fall. So there's a critical point. Just like here, we have our critical point. All right, pressure rise. Obviously, that's a temperature rise too. Okay, and the pressure increased. Look at the temperature. It increased also. Same pressure, same temperature, same pressure, same temperature. In theory, the only thing that we've changed is the state of refrigerant from vapor to liquid. That's the theory. We have no proof. We enter evaporator coil in a liquid state. Obviously, the pressure is, if it's 135 here, well, guess what? It's 135 here as well. So this is 135 psi. This is 135 psi. And then the vapor saturation point at that is 47 degrees. And here is 47 degrees, just like we have 47 degrees here. Over here, we can say that we are in a vapor state, leaving the coil. Pressure is 135 psi. And the theory is that we have evaporated, but the only values that we have, the vapor is a theory, right? Let's look at the facts. You know that it's 135 psi. That is a fact. All right, so let's go ahead and write a couple things down. This is a fact because that's the temperature related to that pressure. This is a fact, okay? That is a theory. Let's look at some other theories that we have. Okay, this is a fact. We know 98 degrees is a fact. Let's look at the pressure at 305 psi. That is a fact. What is a theory? We know that this is a theory. We know that this is a theory. I can just write this stuff all over the place. Here, this is a theory. Oh, wait, we got a fact over here. We got a fact over here. And so if your vapor is a theory, why are you assuming that the coil did its job? Why are you assuming that any of these coils did their jobs? We know the compressor did its job. We know the metering device did its job. How do we have proof of that? Well, because we went from 135 to 305. That's proof your compressor is doing really good. How do we know your metering device is good to go? Okay, we went from 305 back to 135. The coil didn't do that. The metering device. So the only two things you know that are factual here is my compressor is doing good, and I know my metering device is doing good. But I have no proof that these coils are good. I have no proof that these coils over here are good, because my liquid, the one thing that this coil is supposed to do is change the state from a vapor to a liquid. To change the state from a liquid back to a vapor. And if I just went off of, yeah, my compressor, I have 135 to 305, then my metering device, I went from 305 back down to 135. That is not enough proof that your mechanical system is working correctly. Because we have not proven that you have vapor, and we have not proven that you have liquid. The only way you can prove that is by taking additional readings. And so what we need to do is we need to find out, okay, what is the temperature difference, because there's not going to be a pressure difference. Okay, pressure doesn't change. What is going to be my temperature difference? So let's go ahead and say that we clamped, leaving the coil, and we read a temperature of, say, 88 degrees. Well, then I can sit here and say, okay, well, 98 minus 88, that's 10 degrees. Oh my gosh, that is 10 degrees of subcool now. Okay? Now we have proven that we have liquid leaving the coil, because we have another value to add. We have the subcool value. So that subcool value, okay, it's no longer a question. We now know it's 10. All right, we have condensed vapor to a liquid, and we know that because if we take the temperature related to that pressure and we take the temperature of that line, there is a 10-degree differential, which proves that we have cooled it down. It just proves that we have liquid leaving the coil, because the pressure didn't change, the temperature changed. And so now we now know that there is liquid here. Now if we have liquid here, now we can cook, right? We could take that liquid and we could put that liquid in that evaporator coil, and now liquid can boil. If liquid can boil, then we can have a state change to vapor. And so the only way you're going to know that you're not returning back as a liquid, okay, because vapor is a theory, is to prove that we have boiled off. So we need to know, what is that superheat? So we're going to put down here superheat. We need to find out what that is. And so now each of these coils are going to have their own superheat value. Yes, we're starting to level up. Each of these condenser coils are going to have their own subcool value. I can have one coil that's really dirty, right? Or maybe it's just not getting a good enough heat exchange, right? So if we're not rejecting enough heat off of that, we're obviously not going to condense. But maybe the other coil, it is. So maybe one coil I'm leaving vapor, one coil I'm leaving liquid, so I have a little bit of vapor and liquid leaving. Not good, right? Got to clean these coils, make sure that we're transferring heat off of them. Now, if we take the evaporator coil, all right, we have liquid going into both of them. How do we know that we're leaving from both coils in a vapor state? All right, we have to know that we're leaving from both sections of this coil in a vapor state. And this is not a dual circuit system. That's not what this is. As we start to grow, there are many sections to your coils, whether they're condenser coils or they're evaporator coils. There's many sections. We're to keep going. All right, so if we are reading a temperature difference, right, and that temperature difference is warmer, okay, than that saturation point, then we have proven that we have superheat, which proves that we have a vapor. Let's just say that there are problems with this coil. Let's just say that this coil is not transferring heat very well, and we still have a superheat value. Let's just say the temperature that we read here is 52 degrees. All right, well, 52 degrees from the 47 of the saturation point, that's 5 degrees. So that means I have a 5-degree superheat. That's very low. That's not good for an air conditioner. That's great for a freezer. Excellent for a freezer. Not so great for a cooler, which we'll get into all that stuff on other videos, but not good at all for an air conditioner, right? And so we got to have different superheat values when we're dealing with freezers, coolers, and air conditioners, because that's low temp, medium temp, and high temp. We'll get into all that. Let's just first understand that we have to get into any of that stuff and be good at it. We have to understand that we need to know all of our values. All right, and that's what's going to make us at the very top of our game, right? And so, but even if 5 degrees superheat wasn't enough, it's still enough to tell me that, guess what? I'm not a liquid coming back. I'm not a liquid until I'm 0, right? And so when you tell me that I have 135 psi and the saturation point is 47 degrees, vapor's just a theory. Because what if I only had 47 degrees I'm reading here? Well, then that's 0 degree superheat. Well, maybe that's not vapor, but now that's liquid coming back. I have liquid going in, I have liquid coming back. All right? But if I read 52 degrees here out of the 47 saturation, right? Now I know that I have this vapor saturation point and this vapor line temperature has a differential there, and that differential is going up, not down, right? Then I know I have a superheat. So that proves that vapor is no longer a theory. Vapor is a fact. And I have to have vapor coming in, and I have to have liquid to meter, right? And so there's a lot of confusion on this. I don't know where it all comes from. I'm trying to clear it up as much as possible. Let me go ahead and erase this. We're going to do it again. I'm just going to add more circuits to our refrigerant circuit. All right, so we're going to go ahead and add some more coils. We'll go ahead and put 4 sections of condenser coil here. We'll go ahead and do 4 sections of evaporator coil. Now what you see is you just see one coil. You don't really see that there's 4 sections to this coil. Right here you just see one coil. This is one condenser coil. one evaporator coil. That's really not how you should look at this. You should look at how integrated your coils are. So let's just come out, discharge. We're going to hit our process tube, and we're going to come into the coil in several different areas. We're going to say we're going to come into this coil. We're going to come into this coil. We're going to come into this coil. And we're going to come into this coil over here. Let me do that a little bit better. Okay. And so this is the discharge coming in. We'll give you another example. We'll say that this time we're at 290 psi, which has a saturation temperature related to that. Let's see, 290. I wrote that value down. That's 92 degrees. 410A. We'll go ahead and put 410A over here. Okay, so at 290 degrees, I'm sorry, 290 psi and 410A, the temperature related to that saturation point is 92 degrees. So I'm going to go over here and do the return line on the evaporator coil. All right, so I'm going to come over here and say that leaving the coil, we're going to have another process tube here. This process tube will come all the way over here and come back to the compressor, and it's going to leave the different sections of the evaporator coil. Now it's starting to look more like the coil that you're familiar with. That coil will be, has all the process tubes and all the other tubes and stuff like that. So we're going to go ahead and now do the liquid line. That's the only piece that's missing. We've done all the vapor lines, right? We've done all the vapor lines. All right. And so leaving this coil, I'm going to go ahead and say, I'm going to come out of the coil in 3 or 4 sections. Tell you what, we'll come out of the coil that might be a little confusing. Let's do it this way. There we go. And so what I'm going to do here is I'm just going to come out of the coil and tie into my liquid line, just like that. So I got 4 sections of a coil. I've got 4 inlets. I've got 4 outlets. We'll go ahead and put little arrows on all this. Okay, and keep putting some arrows on this. And we're coming in, and obviously the pressure has not changed. We're still 290 psi. We know our saturation temperature related to that is 92 degrees. So we have no proof, but yet what we know is this is supposed to be vapor, and this is supposed to be liquid. You just don't have any proof because all you're reading is a pressure with the temperature related to that pressure. All right, we're going to come out of this dryer, and we're going to go to our metering device. Okay, out of that metering device, we're now going to go into the coil. We're going to go into 4 different sections. So now we're going to say we're going to come in here. We're going to come in here. We're also going to come in here. And we're also going to come in over here. Starting to look like the coil you're familiar with now. All right, so what do we know? Okay, here's what we know. Let's go ahead and look at our couple things. All right, we have pressure changes here. All right, if we're 290 psi in liquid here, well then we know we're still liquid over here. Right, all these are liquid states. Right, that's the theory anyways. Right, the only thing that's changed is the pressure. And so let's go ahead and give it a value. We'll say that we're at 115 psi. All right, so everything's at 115 psi. Okay, and so if that's the case, the pressure doesn't change over here. It's still at 115 psi, which means over here we're at 115 psi. But the theory suggests that this is a vapor. Well, you don't know that because the theory also suggests that you metered liquid and liquid is in this coil. So how do you know that we're at 115 psi vapor? You don't. The only thing we know is we had a pressure drop and the temperature that's related to 115 psi is 115 psi, 39 degrees. So we know that our saturation point on these is 139 degrees. So I have 290 psi liquid here. I have 115 psi liquid leaving. I have 92 degrees liquid going in. I have 39 degrees liquid leaving. All right, that's the only thing that we know. We don't know if we're vapor here or if we're still the same value that we had when we entered, right? Because we don't know if this evaporator coil is doing its job. We just don't know. Let's go ahead and put the value over here. This is 39 degrees. And so we're also going to come over here and we're going to say vapor. So let's look at a couple things. Here we have a pressure rise. We also have a temperature compressor did its job. We know that. That's a fact, right? Here we have a pressure fall or a pressure drop. We'll go, all right? We also know we have a temperature fall or drop. That's the only thing that we know. How do we know that we really had liquid here and we really had vapor here? I mean, we didn't know that when we had one section of coil. We didn't know that when we had two sections of coil. How are we going to know that when we have four sections of coil, or six sections of coil, or 8 sections of coil, or 10 sections of coil? Because when you get into the stuff that you're working on, it's just more sections of coil. And we'll talk about that more when we get into coil technology. And so this is just a simple way to try to better understand how these facts aren't always present until you get more data. And so here, we can say that this is a fact. Here, we can say that this is a fact also. That's a theory. I'm just going to put a T for theory. All right. Matter of fact, we'll just use F for fact and T for theory. So we'll say fact, T for theory. Here, 39 degrees, we're going to say that's a fact. 115 psi, that is a fact. Vapor, I don't know, that's a theory. Okay, well, nothing changed here, still the same pressure, it's going to be the same pressure all the way back to this point, right? So 115 psi, what is that? Okay, well, that's a fact. Put an F there for fact, 39 degrees. That's a fact because if I'm using 410A, 39 degrees, that's the saturation point of 115 psi. But it's in a vapor state? I don't know. That's a theory. I don't have enough information. Okay, let's go over here. Okay, it's the same psi and saturation point all the way back to this side of the metering device. So all of this is fact, liquid, that's a theory still. Okay, 39 degrees, that's a fact. 115 psi, that's a fact. Liquid, I don't know. That's a theory. 92 degrees here, that's a fact. 290 psi, that's a fact. Liquid, I don't know, that's a theory. It's just a theory. So how am I going to know? How can I test that that liquid and that vapor, okay, aren't theories? I've got to know another value. It's called a line temperature. What is my line temperature? What is the line temperature here? Okay, is that line temperature lower than 92 degrees? Let's just say it's 88 degrees. Okay, well, now I have the difference between 92 and 88. I have a 4-degree differential, which means I have a 4-degree subcool. Now I can say that this liquid here, well, that's a fact. This is now a fact. Okay, which if that's a fact, then that means that liquid here is a fact also. So that's a fact, and I now know that that's a fact because I know that I am liquid leaving, because if the pressure didn't change, this temperature is related to that pressure, but I'm reading a lower temperature, obviously I have cooled down that refrigerant, which proves that I am liquid leaving my condenser coil. So I did condense vapor to liquid. But how do I know that I didn't come back to here, okay, in a liquid state and leave in a liquid state? All right, how do we prove that? Very simply. Let's go ahead and look at my line temperature, okay, and let's just say that that line temperature is, let's just say it's 54 degrees. Okay, well, the difference between 54 and 39, let's see, that's 10 plus 15, no, 10 and 5, looks like it's 15 degrees. Yep. So $15 degrees. All right, so if my superheat is 15 degrees, then I have a fact now for vapor. So we're going to go ahead and erase some of these little questions here and say that, yeah, it is vapor. We know for a fact it's vapor. And it's really that simple. And so if it's vapor here, well, then that means it's a fact that it's vapor leaving. Okay. And so, and it's really just that, and everything else is just more of the same stuff. It's just more of the same stuff. And I have other ways to simplify this and explain the superheat, subcool, and all that. This is just an introductory of what we're going to talk about as we start releasing these videos and we start getting into everything else. And it's like I've said that our industry, you know, we have issues where we kill compressors. Well, if this compressor is designed to pump refrigerant in a vapor state because there's oil in here that's being lifted up and it's lubricating these mechanical parts, so there's no additional friction, right? I mean, we have enough friction. We're going from 115 psi to 290 psi. The last thing we need is to have no oil in that process, because if that's the case, this compressor is not going to last very long. And how we lose oil is when we overcharge systems and we have so much liquid coming into here and liquid returning. If that refrigerant is not in a vapor state, okay, then we will kill this compressor. All right. If we are not in a liquid state leaving the condenser coil, then we're not going to do a very good job of transferring heat. So if it's undercharged or if it's overcharged, we're going to have issues. And you're not going to know if it's undercharged or overcharged if you're just looking for pressures. Because as things change throughout the day and the temperature changes, all right, and every coil is in a different state of condition as far as fin condition. You can't rely on pressures. You can't rely on the theories. You have to be able to test to see how the system is performing. And the only way you're going to know that is to add more value and get more data here. There's a product out there that we utilize in our trade, digital gauges, Esman gauges, things like that. They give you these values. As long as everything's reading correctly, then you can actually determine very quickly if your system is functioning properly as the manufacturer built it. All right, that's going to be enough for this. I know this was a little confusing in the beginning. You're probably wondering, do I stay on this video? Do I watch this all the way through? Is this video going to teach me something? I hope it did. There's a share button right there. Go ahead and push that out to your buddies. Go ahead and share it to them. Don't hold this knowledge in. Leave me a comment. Tell me what you think. I read those. This doesn't mean that it's an air conditioner. This doesn't mean that it's a cooler or anything like that. Obviously, it's not a cooler or a freezer because of the type of refrigerant we're using. It's 410A, which is a high temp coolant. However, as far as the theory goes, the simple refrigerant cycle goes, it works the same on anything. Just change the refrigerant out, and all of a sudden you have different values. But as far as what's supposed to happen, a pressure rise, a pressure fall, vapor to liquid, and liquid back to vapor, none of that changes. That's all the same. Doesn't matter what you're working on. All that's the same. All right, and we're just going to keep going at this and just keep leveling up. So leave me a comment. Give me a thumbs up. I need that to help support my algorithm. Okay. Subscribe if you haven't done so already. And stay safe and stay tuned.